to do. Okay, what I'm going to go over today is this old test. Now this is only on carbohydrates. So there is a companion, excuse me, companion version on carboxylic acids and excuse me again, and lipids. So the first one I'm going to do is do this carbohydrate lipids. Now, this is in your Canvas files under test related practice test or old test. I forgot what the name of the folder is. Okay, so first question. Does someone have a question? Okay, so it says describe two similarities and differences between these molecules and galactose. Okay, so there's oleic acid and this ribose sugar. Okay, so galactose, let's do galactose really fast here. And let's do beta galactose since this is beta ribose. Okay, so let's look at the differences. 5 versus 6 membered ring. Five carbon versus a 6 carbon monosaccharide. All right. Anything else you guys notice? Well, the masses are going to be different because you have 5 carbons versus 6 carbons. Oh, that's probably about it off the top of my head there. Okay, let's look at
Can we mention the difference in the alcohol groups?
say again about the alcohol groups.
Yeah, can we mention that as a difference?
One thing you can say is the number of alcohol groups. Sure, that's a good idea. Was that what you meant?
Yes.
Yeah, good. Yeah, good. Okay. Okay, so the name of this file is This was a take-home test, so let's see, where is it now? This is the name here. Then I converted it to a PDF file to load onto OneNote. So if we go back to I think this is it here. Let's open it and make sure. No, it's not. I'm going to put it on again. Uh, yeah, I need to move this down further. I'm gonna stop sharing for a moment and fix this problem. I'm sorry, this is kind of confusing here. Hold on a second. Yes, I know there are a lot of files there. I just wanted to give you as much opportunity for practice. That's why there's so many. I agree with you. There are a lot there. Let me just real quickly though. Okay, so look for the one practice. If you do a search up here, I'm gonna pull up one. Okay. Of course, you want steam. Okay, so we go under practice here, practice test. And I reloaded it and renamed it so it'll be easier to find. Just do a search on one space practice and it'll come up. Okay. I'm sorry for this awkward. Okay, so it was Callie, right? That was looking for the test.
No, I found it.
Okay.
Before that, I was just saying that there's like a lot to go through and it's kind of hard to like be able to use them to study just because there's so many of them.
Well, I could erase them all and just put a couple on. I just wanted to.
Maybe don't erase them all, but maybe like you could put like the ones that you think would be like the most helpful at like the top of the files. Then we could like know to use those maybe, and then also use the other ones after. But
Okay. Well, what I'll do is rename the ones that I'll put a one at the front of the file name, the ones that would be good to practice. And then it'd be easy to do a search on it. For example, just do a search on the number one.
yeah, okay, yeah, that'd be helpful. Thank you.
Yeah, see. Well, it's got all this Chem 131. That Chem 131 was the name of the equivalent course up in Tacoma Community College that I taught. Okay, so let me write that down. So I've got quite a to-do list on my day off tomorrow. Okay, okay, so let's continue with this. All right. So you guys did a good job on the differences. Let's look at the similarities. One, well, one other difference on the this is related to number one. One is a furanose. Versus furanose. 5 versus 6 sugars. So 1 and 5 are related. They're not the same, but they're related. And I would count those as differences as well. Okay, similarities. Well, what about they're both reduction sugars. They have a hemiacetal at anomeric carbon, which would be this guy here. Okay. And we know it's a hemiacetal because we go OCO, so that's a yes. we have an OH present, so that's a yes. And there's a hydrogen here on both of them. So it's a hemiacetal. Okay. I mean, you could say they're both biological sugars. They're both D configs versus L. Oh, what else? They're both beta. Anything else, you guys? Okay, so let's look at galactose again here. And so galactose versus oleic acid. Most obvious difference is that. So masses different. Um, More polar. Um, Oleic acid has a double bond. Okay. Any other differences you guys can see? Okay, let's look at similarities. They're both very polar. The sugar is more polar than the acid, just because the acid had that long tail. Particularly if the pH is alkaline, which forces the form, which is ionic. Um, both biologically important. Let's see what else. I mean, oleic acid and galactose are very, very different molecules. Can anyone think of any other similarities? Okay. So, I'm going to make this smaller. Okay, what polysaccharide has a beta glycosylic linkage? We talked about a number of them. Which is the only one that had a beta glycosylic linkage? That is cellulose. It is classically, it's not considered a reducing sugar, but there is a catch. What would the catch be if I said this is not a reducing sugar? And this is a tricky question. Anyone have any idea what I'm talking about? Okay, so this is what cellulose looks like. Okay, so this is a beta 1,4 linkage. And these are glucose monosaccharides. Hey, Google, office lights. I don't know why Google decided to turn off my lights. Okay. So what does this look like? So this is the last. The last glucose in the chain. What's that? Besides being glucose.
Are you referencing to it's not attached to the primary carbon?
Your connection distorts your audio. Say again.
Are you referencing to it not being connected to the carbon, the primary carbon?
No, it is connected through the beta-1,4 glycosylic linkages. But what I'm pointing to here is a hemiacetal. At the very end, the head end of the glucose chain. Now, the cellulose could have 1,000 glucoses in it, but at the very front of that is glucose, and the anomeric carbon right here is a hemiacetal. So when people say that starch and cellulose are not reducing sugars, they really are reducing sugars, because out of the thousands or so monomers in that chain, the first one is a hemiacetal. Hence, it can open up, be oxidized, give a positive Benedict's test or Tollens test or a number of other oxidative tests. So that's where that tricky question was going, is you were looking at the very first glucose. And its anomeric carbon is not linked to anything else, so it is in the hemiacetal form. Does that make sense? Okay, let's see, where are we here? Okay. I'm presuming everyone's not saying anything, so I'm presuming that you guys understand that. Okay. All right, so it says, why will a triglyceride hydrolysis in an alkaline solution hydrolyze? Okay, that's called saponification. And what happens is the esters are, let's see this. So the esters are reverted back to the acid salt and the alcohol from which they were formed. Hey, Mia, are you okay? One of my dogs, I think, just. No, he didn't. It sounded like he barfed on the floor, but he didn't. Good boy. Oh, okay. All right. Does everyone make sense on that? So when the esters come apart under alkaline conditions, that's called saponification, and they form their acid salt, not the acid salt in the alcohol in which they were created. Okay. Describe the molecule below in terms of the following. Okay. What monosaccharides make up this disaccharide? Okay, well, this is maltose. And maltose is made up of 2 glucoses and with a alpha 1,4 linkage. And what was the other question? It's reducing sugar. So yes, because this is a hemi acetal. Okay, we can use Collins, that's what's silver. And use Benedict's. That's with copper plus 2. Okay, so I'm going to do and the glycosylic linkage is the alpha 1,4. Okay, the reaction. Let's do the reaction over here. Okay, so that is maltose. Once it opens up, because there's a hemiacetal on the right-hand glucose. And let's do Benedict's. This is still in the week of the 23rd. So Monday lab people will get their tests on Monday, Wednesday lab people will get their tests on Wednesday, just like the first test.
Wait, but will it be on the 23rd or is this following Monday?
Well, what's the date on the next Monday?
16th,
Okay. What's the date on the next Monday?
23rd. So I was just wondering, like somebody just asked in the chat, we're not moving it or pushing it a little bit back. I mean forward, because we're on top of our schedule. Somebody was worried that you might bring the test a little closer than the scheduled date on the syllabus.
Yeah, the syllabus or the lab schedule says test 2 is in the week of the 23rd, right?
Yes, yes.
Okay. And the 23rd is a Monday, the 25th is Wednesday. So the 23rd will be Monday's test people, 25th will be Wednesdays, just like the first test. Is that the question?
It makes sense, yeah. No, we were just wondering if you were going to like move it up by a week. We were worrying that it would be on the 16th and the 18th. But now that you explained that you're still going to follow the syllabus, it makes sense. Thank you.
Okay, well, the reason why I want to keep it there, I'd like to review a lot. I mean, this chapter is a lot more, or this unit is a lot more than unit 1. So I'm going to give lots and lots of examples and working through them. That's why I'm going to keep it there. I'm going to make sure everyone is comfortable with this material. Okay, so let's continue on here. Okay, so we have maltose. Maltose, the right-hand one is a hemiacetal that can open up. And when it does open up, it presents itself as an aldehyde. Now that aldehyde can be oxidized. And this is in an alkaline environment. And when it gets oxidized, it's oxidized to the acid salt plus copper 1. So the copper 2 for the cupric is reduced. And the aldehyde is oxidized. And that copper is copper 1, not copper 2. Okay, and it's in the form of that, which gives it that orangey color, orange rusty color. Now, if we did Tollens, that's what silver 1, and that would go to silver metal instead of the copper. Exactly the same reaction as far as the sugar goes. It's just the oxidizing agent is different. So that's what this here is about. Okay, so what test you can use? Tollens or Benedict's, and that's the reaction. Okay, how can a monosaccharide such as glucose have both an open and closed form? The hemiacetal is present. No hemiacetal, it does not open up. Okay, lipase digest or hydrolyzes fats carbs, and specifically sucrose. So in your saliva is sucrase and amylase. So as soon as you hit a carb hits your saliva in your mouth, it starts to hydrolyze into its individual monosaccharides. So you immediately generate glucose, fructose, so if you are eating like a cracker, for example, that's a classic test for looking at amylase and sucrase. It almost instantaneously be converted to glucose and fructose in your mouth, even before you swallow it. Acts very fast. Lipase and the pH requirements are around 7. Lipase pH requirements are around 2. And lipase is, excuse me, also at 7. Lipase is in the small intestine. These guys are also located in the small intestine. That's why we're looking at a pH of around 7. Protease, located in their stomach. And that requires a pH of 2. We're going to talk a lot about enzymes. And basically, there's something called activity associated with an enzyme, and that's how well it works. And enzymes require a certain pH and a certain temperature to function properly. When your pH is off or the temperature is off, the enzyme's activity falls way off. What I mean by activity, what I mean by that is, what is the enzyme supposed to do? Is the enzyme supposed to hydrolyze the fat or hydrolyze the carb? If the pH is off, it won't do that very well. Okay, draw examples of an unhealthy fatty acid isomer and unhealthy, a healthy one and an unhealthy one. Okay, well, omega-3s are considered healthy. Omega-9s and omega-6s are considered less healthy. So a less healthy one would be like stearic acid. Which is a C18 saturated fatty acid. A healthy one would be like linoleic, alpha-linoleic acid. And the difference is going to be here. Is where the unsaturation in the fatty acid is located. This is what's the linkage in the top question. You're talking about the first question we went over? On this page, so up here. Okay, that is alpha 1,4, which I mentioned here. So this linkage here would be an alpha 1,4. You're welcome. Okay. All right. So is the following saponifiable? Okay. Is an ester present? Yes. There it is right there. So the answer is yes. So in an alkaline environment, we end up with this guy here, which would be palmitic acid. Let's see. Okay, so it's 16 carbons, no double bonds. Looking at and this would be the acid. So we're looking at a 18 alcohol, octadectanol. Okay, so there's 1, 16, 1. That's 18 carbons. 1, 14, 1, 16 carbons. So this is the acid salt, and that's the alcohol. So that would be a wax. Okay, consider the molecule below. I think I mentioned this molecule in lecture, if I remember right. Okay, well, we've got alcohols here. So to make an alcohol, the precursor would be this giant thing from an alkene. So the alkene can be, you know, like here, or there, or there, or there. What else we have here? We have an amide. We also have an acid salt. So one reaction could be plus an acid, which would then protonate that. We haven't talked about amides, that's unit 3, but that's an amide, which is instead of an ester, it's formed with nitrogen. And so that wouldn't be. So we have these reactions, the alcohols, and we have the acid salt being converted to the protonated acid. And to draw these, you just draw this whole thing out. Now this is a take-home test. So you have lots of time to draw this stuff. So this is a steroid. The basic steroid structure. Okay, and then this so we'd have this whole thing, only instead of an OH here, we'd have an alkene over here, or over there, or over there, or over there, plus water to yield these alcohols. Here we'd have the whole, for the second one, we have all this plus an acid would yield the protonated acid. And this here would be the structure here. Okay, so that's where I was going for. So precursors are the molecules from which you start with. You end up with what you want to end up with. That's what I mean by a precursor. Okay. Emulsifying agent. Okay. Do we have a polar plus nonpolar areas? Yes, we do. We have the ionic and or let's see, let's do something like that here. This would be the polar part. And this other part would be the non-polar part. And is this a steroid? So it contains the basic steroid structure. Okay. So basically, big giant biological molecules are made up of parts of smaller ones. And the first thing you do with a big giant molecule like that is look at what are the functional groups. Functional groups. Okay, we talked about alcohols, we talked about acids and their corresponding salts. We've talked about a tiny bit on this nitrogen version of the ester. And I wouldn't expect you to know that. But these others definitely I would expect you to know. Okay. So arachidonic acid is a precursor to prostaglandins. And we talked about there's two kinds of prostaglandins. So now this is an acid. So an acid in low pH is protonated. So this would be what it looks like. And then it would look like this. And pH greater than 7. Okay. So this would be non-ionic. This would be ionic. So basically, you put an acid in alkaline conditions, it becomes even more ionic, more polar. Okay. So we have a ester in a alkaline environment, which is the alcohol plus the acid salt. So these guys are 116 carbon, saturated fats. We have one. This is a hexa. Sodium hexadecanoate. And then what? So it says, ration go further, list all steps. So we're going to oxidize this, we're going to get no reaction. Okay. And here we have the arachidonic acid again. And this is the prostaglandin. So there's a number of steps that it goes through. It's all enzymatic. Remember we had the COX-1, COX-2 enzymes. Okay, so what do we got going on here? Okay, we've got a ketone, got an alcohol, we've got an alkene, got an acid. Okay, to get an alcohol, we're going to come from an alkene. To get a ketone, we're going to come from a secondary alcohol being oxidized. To get an alkene, there'd be no change here. It starts with an acid, ends with an acid, there'd be no change. And this has got some unsaturations, the arachidonic acid. So it's going to have some unsaturation there. But basically, we're looking at the alcohols and the ketones. So this is a secondary alcohol as well. Okay. So basically, in this one, I just wanted you to point out stuff. So this is a beta galactose. Beta because of this. So that linkage is going to be a beta 1 linkage. And we don't know the carbon numbering up above, so we're just going to say a beta 1 linkage. See, we have that would be an acetal. Okay, so we have OCO, so that's a yes. We have no hydroxyl group, and there's an H there, so that's an acetal. We have a secondary alcohol. We have this amide thing again here that keeps coming up in biological molecules. Carboxyl group would be this guy. Okay. Okay, this molecule is part of your fat. And what it does is it resides in the fat that surrounds a nerve, insulating it. And what happens if anything destroys that insulation, the nerve can no longer function. And that's what happens with, let's see, this is adrenal lupus dystrophy, I believe, ALD. They made a movie out of this. I can't remember the name. It was some or other oil. Did anyone see that movie? It's with Susan Sarandon and Nick. This was a long time ago, about 18, 20 years ago. Anyway, if a young boy was diagnosed with ALD, they usually didn't live much past 5 or 6. And the parents got involved with that, and they felt that the medical industry wasn't doing enough. And they started doing their own research. And they ended up actually finding not a cure, but a treatment for ALD. And their son lasted until he was like 35 instead of, 5, 6 years old. And his it's really a tearjerker too. If you ever get a chance to, in fact, let me look it up really fast. This is a really good movie. Lorenzo's Oil, 1992. Yeah, and Lorenzo's Oil was really simple. If anyone would like to do their project on this, more than welcome to do it. And watch the movie first and see if and make sure you have a box of Kleenex close by. It's a real heavy duty emotional movie. So anyway, so Lorenzo's Oil. Lorenzo's Oil movie. And Lorenzo's Oil is what fed the rogue enzymes that was destroying this particular chemical in the sheath. So the enzyme ended up hydrolyzing Lorenzo's Oil instead. It was really a cool movie because it shows what our parents' advocacy can do, even though they're not MDs. They still were able to make a huge difference in that boy's life. Okay, all right. Okay, so here's the molecule. Basically, we got a sugar here. We've got phenylamide again. We have an alcohol, OCO. That means it's a yes, no, yes. So it's OCO, yes, no OH, and then there's a hydrogen here, so this is an acetal. This is the amide here. So what sugar is this? Now the problem is this is the anomeric carbon on the left rather than right. So you need in your mind, flip this over. So that's galactose. And because this O is going up, it's beta galactose. The linkage is going to be a beta 1. We're not sure what the carbon naming is for this here. So whatever that carbon number is. Okay, all right. So that is that test. Now this test had a lot of biochemistry in it. So possibly a lot of students had issues with this question about the precursor part. And I used to give a lot of take-home questions about biological molecules like this and about how you go about synthesizing them. And you'd have to come up with some precursors. So I just wanted to get students used to looking at complex molecules that are made up of functional groups that we've studied individually, just putting them all together. And this is what a either a biochemist that's trying to synthesize this, or a biological oriented organic chemist trying to synthesize this in the lab. Now this is synthesized in the body by a whole series of enzymes. Enzymes are magic. And we're going to talk a lot about enzymes and their active sites and why those active sites are very sensitive to both pH and temperature. In the active site's modified, the enzyme can't function. So whatever the functionality is of that enzyme is going to not work anymore. So if the enzymatic reaction is really important, then you suffer. So, all right, are there any questions about kind of this test? What's nice about this test is it pulls together a lot of the stuff we've been learning on a small scale. The polar part is just the NOA, Na plus. No, that's half of it. The other half is the acid salt. I'm trying to figure out where is. Let's see. For example, here. So if we have an acid salt, we have to have a cation that goes with it. Because all ionic compounds have to have one of each to make the ionic compound neutral. So if something's positive, something has to be negative to offset it. So this is the ionic part. Both the sodium cation and the acid salt itself. So when you say acid salt, you always have a cation against that negative oxygen from where the proton was pulled off by the base. Did that answer your question? Good. Okay, what I'd like to do is look at I'll tell you what, I'm gonna end this today. On Monday, I'm gonna go over another take home or another practice test, and where it looks at more the lipid side and the carboxylic acid side. But this one was kind of more of a aldehyde ketone carb focus. I want to make sure we give equal time to the carboxylic acid esters and lipid side as well. I think the carb side is a little trickier, probably a 60-40 against the esters and lipids subunit. Okay, so are there any questions? We're going to be working in groups of 6 today in the lab because we need to use the hood when we're making our soap. And there's only 3 positions in the hood. So we're going to be groups of 6. There's a lot of stirring. You're going to be stirring your soap for at least 30 minutes, possibly more. So we're going to be trading off. That's why we need a number of people in the lab, in the group. Okay, so any questions? Last minute questions? Okay, so why don't I see everyone? Now, Monday lab folks, if you have something you want me to address regarding your lab write-ups or something like that, feel free to come by and hopefully I can get your question answered. And have you looked at your lab? Have I changed the grade on your lab? Okay, was your lab, did I comment on why your grade is not changed? It might be because your uploaded file did not have handwritten in your lab notebook that you scanned. Oh, you talked to me already about this, and you mentioned you were ill. So I was going to give you, because you were ill and missed the lab, I was going to give you a dry lab version with the data. Is that what we talked about? Ah, okay. So give me a couple more days to make sure. Well, I don't need a couple more days. I just need to find, you're in Monday's lab, right? Okay. Let me give you some data. So the labs have all been turned in now. So I do have data to give to you. Just keep if I don't do it today, for some reason I forget, email me, okay? And then I'll be sure to get it done. I just have, once lab starts, there's a lot of things going on and sometimes I forget. Okay, cool. All right, everyone. Are there any more questions? Okay, so